video, we shall discuss about specific enthalpy for a two-phase mixture. In the previous video, we looked at the interpretation of a two-phase mixture formula for a specific volume. So in case you didn't check out the video, you can look through the playlist and you watch it. So let's go ahead. Enthalpy in thermodynamics is represented by capital H, and it is equal to the sum of a total internal energy and the pressure of a system divided by its volume. So you can see that the capital H is enthalpy, and the capital U represents internal energy, and P is pressure, and V is volume. So internal energy is equal to the internal energy of the liquid phase plus the internal energy of the vapor phase, and the total volume is equal to the volume of the volume occupied by the liquid phase plus the volume occupied by the vapor phase. And remember, if you've been following the entire playlist, for this entire system, we're assuming a rigid container like water kettle, electric kettle that's using to boil water. Its volume is going to be rigid, it's not changing. And once you have a rigid volume and like the liquid that is within it before boiling and after boiling, when it changes into phase, the pressure from the walls onto that body is going to just be uniform. So that's why you see the pressure here is there's a uniform pressure for both phases, because the pressure from that container is acting uniformly onto the contents of that container, be it an electric flask or a tank. So once you do the substitution, you'll find that you have enthalpy is equal to the total internal energy of the liquid phase plus the total internal energy of the vapor phase, and just like that, you do the substitution, and you collect like terms. You first expand just like this. I'm applying pressure throughout the carrier barriers, and you collect like terms. And once you collect like terms, you realize that this itself is a formula for enthalpy, and this is a formula for enthalpy, but for the liquid phase and the vapor phase, and you get this, such that the total enthalpy is equal to the enthalpy of the liquid phase plus enthalpy of the vapor phase. But we know that specific enthalpy is equal to total enthalpy over mass. So if you were to take enthalpy for the vapor phase alone, you would have it as the specific enthalpy of the vapor phase multiplied by the total mass of the vapor phase, and enthalpy of the liquid phase is equal to enthalpy of the liquid specific enthalpy. Every time you look at a small letter here in thermodynamics, it's representing something that's specific, that's a unit of that property of a mass. So multiplied by mass, and you're going to substitute bulk into this formula. And you will get this. But we know that total mass is equal to mass of the vapor phase plus mass of the vapor phase. Once you collect like terms, you'll find that the mass of the liquid phase is equal to total mass minus mass of the vapor phase. So once you do the substitution here, you're going to get, you will get this, but before that, you already know that this here introduces the quality concept. Let me use some drawing tools here. What do I use? This one right here introduces the quarterly concept. This x specifically. Remember that x is equal to mass of the vapor phase divided by total mass. This introduces the quarterly concept. So once you cross multiply, here's one, you will arrive to this. And once you substitute in this formula, once you substitute this into this formula, you're going to arrive at this. So let's go ahead and you arrive at this formula. You after substitution and the general substitution. Remember we had so subscript F and M. Now you're going to substitute for this M. So you get this here, and you substitute for mg. That's why you get this here. So the other values, you write this on a paper and you do the substitution yourself. That would become more easy. So now once you solve the equation and you bring the like terms out, you factorize the like terms, you're going to have so this is a multiplication, so and it's an addition and it's also a multiplication, but there's this common like term mass, total mass. So you bring it out, and once you bring it out and divide through, you'll have specific enthalpy, and this will bring you to this formula here, which is the specific enthalpy for a two-phase mixture in thermodynamics. So you can pause the video and you derive the formula on your own, and it will be quite simple if you do that. And in the next video, we're going to look at the specific entropy formula for a two-phase mixture. So be sure to check out the video and see you there.